I just want to take you guys through a couple little exciting updates. I guess I'll keep it short. I'm actually probably not gonna work on stream today, but I'll just still show you guys what I'm up to. So, um, here you can see these are little pulleys I'm making. Let's see. So that's just a piece of TPFE tubing. Alright, so it's a little 3D printed wheel with TPFE tubing wrapped around it, and then three little pieces of tape wrapped around that. And because the tape is made of workout shirt material combined with 3M 300 LSE adhesive transfer tape, which looks like this. Just the shirt's pressed on to the tape, and then there's the back that peels off, and then it's sticky tape in between. I just cut them out into little strips. Here's a strip without the tape on it anymore. It's a used up strip. Here's with the tape still on it. So you just peel that off, and then you just stick it onto. You just do like one piece of tape at a time, and then I'm super gluing over that to solidify it, make it stronger, make it hold that shape. And so these are my little pulleys. I'm calling them pulleys, even though they're not traditional. And so one string will go through and then around back up. Another string will go tied around through the center hole of this center wheel thing, and then come down this way. And then this will achieve this basic operating principle where we've got our motor, and it's going to go up and around and then down, and then it's just a compact pulley system where this tubing was drawn as just regular tubing, but I made it more of a U shape and I added the little what do you want to call it? 3D printed plastic donut, a flat donut. I added that just to support the bend shape and set up a bend radius that I felt would be a comfy radius for the string to pass through. I describe it as comfy because if it's too small and the string's basically just making too direct of an angle change, that can be harder wear and tear on the string. So I gave it more of a U shape than what is on this drawing. This drawing was done without putting in the angle of, or like the curvature that would be most comfortable for the rope pulling through it. With that, this drawing was made without that in consideration. Also, the forces pulling down in this direction from the load would possibly bend this to kink it in the center, and it would fold in half, so it wouldn't be able to maintain that like nice sloping shape that you see drawn here. So that's why I needed to actually mount it onto these little wheels. So I've got a bunch of them made, and these will form my compact Archimedes style pulley system. And I'm just making them one at a time here on my clipboard. You can see this one I haven't yet trimmed off the end of the TPFE tubing. This TPFE tubing is what was it? Hold on. It's no TPFE. No, it's not TPFE. I'm sorry. It's PTFE. Is it TP or PT? I thought it was TPFE. This says PTFE. I'm not sure. This could be a typo. PTFE Teflon tube, 0.3 millimeter ID, 0.6 millimeter OD. I bought 10 meters times 3 for $22. It's also considered size number 30. I'm using this for upholstery thread fingers. And so this is my basically muscle thread guidance tubing I've selected. and it works great. Also, this type of TPFE or PTFE, I'm not sure how it's properly pronounced. This type of tubing is used in creating lubricants. There's like TPFE lubricant, which I guess is the same type of plastic ground down to a fine dust, and then mixed with like oil or something, and it creates a lubricant. So this is very smooth, slippery plastic, which is great since we want low friction with our string sliding through this plastic over and over and over for a long period of time. Also, I did a kind of a final drawing here of what the compact pulley system will look like. So here's, let's see if it'll zoom in that far. There's our motor, and then it goes up to a big pulley in the top center. I'll point out what I'm talking about. That pulley it goes up to, and then it comes down. It goes around a little pulley, and then back up, ties off. And then off the bottom of that second pulley, it's going to come down and then go around that one, then tie off up here. And then it's going to come down off the bottom of that, around this pulley, and then tie off up here. And then it's going to come down off this pulley, around, and then tie off up here. Then from this bottom pulley, because there was 1, 2, 3, 4 pulleys, it'll come all the way down to our load, which will just basically go to a finger joint or whatever. So it's a 4-pulley system. It's the Archimedes style pulleys, and each pulley doubles the force. So the first pulley 2x's the force, the second one brings it up to 4x, the next one brings it up to 8x, and then this one to 16x. We might end up adding one more pulley, and it would be 32x at that point. We might do that, but I think the 16x might be fine. Now, the other thing I'll show you guys real quick is the latest on my okay, I'm going to show you the latest design I made. So let me just pull the motor back up here so you guys can see better what's going on. I'm a little bit sick, that's why my voice is off. Okay. So, this device here, which I just highlighted, I'm referring to it as my muscle string guidance hose guide. It basically just slides over the top of a size 140 DC motor, which is this object here. That's the motor. It just slides over the top, and the motor has like a pulley here and a pulley here that I add to it. And so the string winds here. I think the outermost goes counterclockwise, and then this one's wound clockwise. And then the string is wound up clockwise here, and then it comes through it, and then it goes through this hole. And then this top part goes counterclockwise, and then it goes through this hole. And after it goes through the hole, it enters into our guidance tubing, which I created here to demonstrate. Okay. So the string comes out this hole and then enters into this tube, which will be a hollow tube. And I just showed you guys that tubing. It's that PTFE Teflon tubing. It goes through the tubing and then off to wherever we want it. In this case, it's going off to our pulley systems, which will then transfer the amount of force or increase. It will transfer speed to force. So it's reducing the speed but increasing the force. That's what the pulleys achieve. Now, this little outcropping here is so that you can wrap tape around the tubes, the two tubes, and then around the outcropping, and it will basically pin these two tubes to this little plastic outcropping. So you can tape them down snugly so these tubes can't like jump up here or jump down here, like fall out of place, that they'll be kind of locked into place, lined up perfectly with these two holes. And so this keeps the flow of the string coming off this winding all in a nice alignment and prevents it from like taking too drastic of a turn angle. It can turn more gradually. Otherwise, like if you just had the string just coming off of here wild, it would just like come up here, it'd be rubbing on this sharp edges of the motor. It needs to be guided. The string has to be guided so that it's taking gentle turns, so it's not too hard on the string. Also, after I printed out this thing, I realized, hey, how do I tie this down to the motor? Like, how do I actually attach it? If I were to glue it down to the motor, you wouldn't be able to rotate the tubes later. Like, let's say I wanted to take this whole thing. If I wanted to rotate the whole assembly like that, okay, after it was already, like, the motor's already mounted on the robot, but I want to just tweak it and rotate the wheels a little bit, I wouldn't be able to because it's glued down to the motor. So I wanted it to be easy to detach and reattach. And so in order to do that, I added these little grab handles. I'm sorry guys, this is annoying. Center pivot. Okay. I added these little tabs, which 3D print along with it, and you can actually put your upholstery thread through this, and I pull about 5 inches through and then leave 5 inches coming off the other side. I tie a knot, and so I've got a bunch of thread hanging down from this, and then I can sew that thread into the mesh sleeve that I have wrapped around the whole motor. And that way I'm able to actually strap this down by sewing it in, so it's a mechanical connection. I sew it into the sleeve that wraps around this motor. So this is actually sewn on. And I'd like to show you guys one of those 3D printed so you can see how they look. Okay, so I'm going to show you guys how that actually came out in real life. I actually made it, and I attached it, and everything's looking really good. So let me show you guys that next. So here you can see it. It's on this motor. You can see the mesh here. Alright. Okay. So you can see I had to actually wind up the thread on here. There we go. I had to wind up this thread on this outermost part because that handles the extension, and because the robot's finger starts out by default extended, that can be wound up as though this motor had already extended it. And then the flexion portion for the finger, which is in the groove that my pen's pointing at, closest to the motor, should be right here. That's, you can see, not wound up currently. Alright, so here's this guidance, what's it called? Muscle string guidance hose guide that I 3D printed. You can see here's that part, that bulging part that has the two holes in it, and that leads to where we've got the tape around the two tubes which come out, and you can see the little tabs here where I was able to put my string through, and you can see let's see, there's some extra string sticking out, but you can see right here in like a V shape is two pieces of thread coming off of this tab and then sewn into somewhere on the sleeve, the mesh sleeve. And so I did that all 4 times. You can see here it's also tied off in 2 directions so it can't rotate, and it's also tied snugly. And you can actually like pry on this thing. It's not glued on at all, but it doesn't move. It's pretty solid on there. And so that enables the string that needs to line up perfectly with this little pulley area. it guides that string on perfectly. You can see the string coming through right there at the tip of my pen. You can see that little string right there. And the other one's up here somewhere. It's up high. You can't really see it. But it's up there. It's somewhere up here. So yeah, when the motor rotates clockwise, it will flex the finger joint, and when it rotates counterclockwise, it will extend at the finger joint. And so coming off of that, my goodness, what a mess. It then takes a pretty gentle turn. Hold on. Okay, so it comes off of the motor, takes a pretty gentle turn. It's going through the two tubes, and those tubes I taped off like right here. And I actually did something kind of cool on this one. After I wrapped some fabric tape around it, the same tape that I was showing you guys earlier, made of, it's homemade tape made of workout shirt material with adhesive transfer tape, cut out in little strips. I wrap around, and then what's cool about that is you can put super glue on it, and because it's very porous material, the super glue seeps into the fabric and then hardens, and it becomes like a rock. So it becomes like a plastic piece at that point. And so it's pretty convenient for this purpose. And I just tied some string around that. I tied some upholstery thread around this, and then I put some super glue so that it wouldn't untie. And then with the piece of thread left over, I sewed it into the bone an encasement sleeve, which is actually made of 1000 denier nylon fabric with the same adhesive transfer tape on it, and then it's like sewn in this section. You could see some stitches sewing it, but all the bones are wrapped up in this sleeving. You could see like they're coated in sleeve, and that's enabling you to sew parts onto the bone, which is kind of the same way it works in a human body. Bones like have stuff able to sew themselves into it. Like muscles obviously attached to our bones somehow, right? I think it's called like fascia tissue or something. Like our tendons connect to our bones through fascia tissue or something like that. So our bones kind of have like some type of fabric encasement too that attachments can be made onto. So anyways, I sewed this string that I wrapped and glued onto this little tape joint thing. I sewed it into the bone, and so this is snug. Like, watch. Like you can't really you can move it as much as my string looseness is, but it's like locked into here. And so I'm planning to do that like the whole way up the arm. So I thought that was pretty cool. A cool little touch I made. So I've got it tied off the one time. I got to tie it off more times. But I'm basically going to run it all the way up to the top of this elbow joint through these two tubes. You can see I've got more tape off points as I go up the tube. And then this tube is going to turn a fairly sharp turn, and then it's going to attach at this little tab part. I made this tab out of a piece of plastic, and I sewed it off from its end onto this little metal piece here, and then onto this little metal piece here. So you can actually pull down on this pretty hard, and it's solid. Like this thing's not moving. It's all sewn in. It's just a piece of plastic that I wrapped in 1000 denier nylon cloth tape, homemade tape, and sewed all the edges really good. And it's solid on here. And so all my pulleys are going to actually descend from this tab. So they're going to come downward. So this tubing is going to attach to the top of that tab after making a 180 degree turn, but gentle turn. That's why I got plenty of extra slack in this tubing. And then it's going to come down, and then it's going to make all those little turns. And as I said, the pulleys, I custom made these little pulleys, and they look like this. And it's just a little U-turn of TPFE tubing wrapped around a 3D printed little pulley with a little hole in the middle. and so the pulley will raise and lower as the motor turns and draws it in through the string. And these will raise and lower, and then I'll have like 3 or 4 of them, and that will increase the total strength output of the motor by 2x per pulley used. So the first pulley is going to double the strength of the motor. The second one will bring it up to 4x strength. The third one will bring 8x strength. The fourth one will bring 16x strength. So whatever the raw strength of this motor is, will be 16x that. The reason we need pulleys is because we're using just a raw motor. This is not a geared motor. A normal servo motor has a 180 to 1 gearing ratio. So it's like a 180 times stronger than the motor itself at the final output. So you have to increase the strength for it to have any significant strength at all. The raw output strength of a standard DC motor like this is so minimal you can actually grab the shaft with your fingers and stop it from turning easily. They don't produce much natural output strength, but they're extremely fast. They're like 3,000 RPM. Some are up to like 6,000, even 10,000 RPM. So they're fast, but no strength. So you have to gear them down to trade speed for strength. And I didn't want to use gears because I can't fit the gears, because we have to put so many motors onto here in my design, that putting a giant servo wouldn't work. Because, for example, this motor alone is just for the distal tip of the index finger. This one is for the middle knuckle of the index finger. This one is for the base of the index finger. And this one is for the base going left and right, forward and back. So these 4 motors are just for the index finger. Because I'm using so many motors per finger to maximize the strength of each finger and dexterity to be maximum, I have to fit a lot more motors than most people would have to fit, because I'm making my robot much more dexterous and capable than most people's robots. And so I have to create a complex pulley system. And because I'm able to fit the pulleys on the backside of the arm in a very small form factor, I'm able to fit as many pulleys as I need. This forearm, I believe, will have a total of like 200 pulleys, I think, which sounds pretty ambitious, but each motor is supposed to have 4 pulleys per direction. Each motor has 2 directions, flexion and extension of the joint that it is responsible for. So that's 4 pulleys for flexion and 4 pulleys for extension. So that's 8 pulleys for each motor. And the forearm of my robot has 25 motors that are going to be assigned to it, which will handle the wrist, the forearm, and all the finger joints. So that's a lot of motors, and if each motor has, as I said, 8 pulleys, and you have 25 motors, that's 200 total pulleys. So that's going to be really hard to pull off, but I'm off to a good start. It's kind of overwhelming, to be honest, that I have to actually do that, but that's my plan right now. You can see these motors are pretty beefy compared to like a tiny little geared motor or a tiny little micro servo people try to put in the palm of the hand, and they wonder why their robot hand has not got much grip to it. They're using tiny little toy motors. I'm using some pretty beefy motors compared to what they're using, but as I said, these have to be geared down, and so my pulley system idea is intended to do that. So that's where I'm at so far. I still have to finish connecting this tube to this little tab I made at the top, and I'll just be able to stack whole pulley systems like in this region, from here to here. During the whole back of the forearm I'm going to dedicate to tons of pulleys, and I'll just keep adding them. The first motor I'm going to add all 8 pulleys, and then I'm going to do testing, so you guys will get to see the distal joint of the index finger moving like this. It's just going to be that, and so I'll definitely do that on stream. And then if I'm happy with that, like if it's too weak, I'll have to add another pulley, and I might even have to do some redesign work on the output of this pulley system, which would suck because this took a long time to like actually get together and get it working. So that's gonna be a headache, but it's whatever we got to do. You know, there's gonna be some trial and error. So that's where I'm at so far. I'm making good progress toward my first set of pulleys for my first motor, and just mounting this motor and doing all the electrical work for it and labeling all the electrical wiring and setting up the pulley system for it, designing the pulley system for it. It's just been like, I swear, like maybe 40 to 60 hours of work just on one motor, which is just gonna do this. That's it for one joint, one finger. But that's the price you pay when you're trying to customize everything and do stuff that's not off the shelf at all and super custom. And I think that once we get past some of those early hiccups, it's going to go a lot faster. Like when you are building a new product, um, the first time you make the first prototype can take you like 100 hours, but then once you start making like the second and third iteration of the product, it gets way faster. Like one product I invented, it took me, I remember, about 30 hours to make the first one of them, of this product I sell. And then now, years later, it takes me about 3 hours to make the product start to finish. And so that's 10 times less time. So if the first motor takes me like 30 hours to get it all built and working, then, you know, a couple of years from now when I'm on my 50th motor I'm doing the same stuff with, it should only take, let's say, like a few hours maybe. And that's not too bad. If it takes 3 hours per motor and you have 25 motors for the whole functionality of the whole hand, 75 hours to make an entire like super complex robot hand is not that bad to me. That's super worth it. But yeah, it's like all the R&D, all the planning, all the design work, figuring out where to put everything, figuring out how to make a miniature pulley. It's like a lot of problem solving. It's frustrating to talk with a runny nose when you're sick and a cough. It's so annoying. So this was a pain to give this presentation with being sick, but I'm glad I got to give you guys a little update there. You said, are you worried about heat? You can check a whole bunch of videos I made about my design for cooling systems for the robot on my YouTube channel, Art by Robot on YouTube. I have a whole playlist for my humanoid robot building playlist, and it's got like 150 videos on it because I've been working on this project for 7 years on and off. And I cover in great detail my designs for the cooling systems there with schematics and drawings and everything. Are you going to use the same method for elbows and shoulders? Yep, same exact method for everything, except for like those bigger type muscles, I'm going to be using brushed DC motors instead of plain DC motors. I mean brushless instead of brushed. So brushed motors are 70 cents each, and so it's really economic to do for like the fingers and stuff. But the brushless motors are much better for the bigger muscles. And I'm even tempted just to switch to full brushless for everything. I kind of feel bad using brushed motors at all because they're so inferior in so many ways. But I couldn't find miniature brushless DC motors in about the size I wanted that were in runner. There's some outrunner brushless DC motors, but not in runner that are in that small size, like a DC size 140 motor is. So I couldn't really find that. I'm sure it might be out there, but I couldn't find it on eBay, which is where I bought all my motors. And it's possible these brushed DC motors actually will work fine. But I am a little bit concerned they might not be up to the task. And I have to be prepared within myself to actually remove all of the motors I put onto here, basically start all over if I decide um, these motors are not going to work. And I'm willing to do that. You know, building a robot that's super sophisticated humanoid robot, you're going to sometimes have to redo some stuff because that's trial and error. That's part of the scientific process. So, I think that was a pretty good little update. But yeah, heat is a huge, huge concern. So I've spent a lot of hours, a lot of time designing very complicated cooling systems for the humanoid robot. And those cooling systems I'm not going to be putting in right away, but they are built into my blueprints for my 3D designs and 3D software. I blueprinted in actually multiple different types of cooling systems. I have water cooling system planned and an air cooling system planned. The robot's going to have artificial lungs to handle air circulation within its body. It's going to have a silicone skin body. It's going to look completely realistic. Um, and it should be able to pass for a human. That's what I'm going for. I want it to look completely real. And then the liquid cooling system is also very important. I think they'll complement one another, the two different types of cooling. So, I guess that's that for the update. I'm not going to do the work on stream just because with the more limited time I have to work on it, fielding questions and stuff isn't the most efficient use of my time. When it's time to work on the robot, I want to really maximize that time by having full concentration. So I just like listen to the audio Bible or some music while I just really focus on getting the work done. So I'm only going to stream updates like this where I explain like certain design updates and actual implementation updates, and then I can also stream like testing and stuff like that to demonstrate progress, milestones. So I just wanted to share that with you guys. Alright, well, peace out, guys. How often will you be online? I have no idea. I don't really have a set schedule. It's totally random. Thanks for the update, and thank you, Rizzo. It was a pleasure to do it. Thank you guys for asking questions and hanging out with me for a little while. I'm going to go back to watching the Tesla AI Day 2022, where they announced their humanoid robot. People told me don't build a humanoid robot, just wait till you can buy one. And it's like what they told me is coming to life. Elon Musk is saying he's going to sell these for under $20,000. That's something I think I could afford if I start saving for it. But, and I know this is controversial, but I think my robot's going to be a lot better than theirs. And I'm not saying that out of pride or whatever. I have a very specific reason for that. They're just building a more simple robot. Mine's going to be a lot more sophisticated. I'm not saying I'm a better engineer than they are either. I'm just saying that their goal is lower. I've just set a much higher bar. My robot's hand is going to have 25 actuators. Their robot's hand is going to have 6 actuators. So how sophisticated can it be with hands that only have 6 actuators? Like, that's going to cripple its total usefulness as far as what it can achieve with its hands. Can it play piano? Can it perform a surgical procedure? Can it sew? Can it play a guitar? Like, you can't do that with 6 actuators. It's impossible. So they're limiting the design complexity to make it easier to mass manufacture. They're not going for something that is as complex and capable as the design I'm going for. And so that's why my robot's going to be better than theirs, because it's designed to be more sophisticated. I'm not saying it's because I'm so much better of a designer or something. their design is better than mine for the purpose their design is intended, which is a general purpose, dumbed down, simple humanoid robot, comparatively speaking, much more simple than mine. And it will just be able to do very basic things like picking up a box, maybe doing dishes. I don't know how much stuff it can even do. Um, Whereas my robot would be able to build another robot. My robot would be able to perform a surgical procedure. My robot would be able to climb a mountain or do whitewater kayaking. My robot is going to be able to do gymnastics. That's a whole other level than anything they're even imagining for theirs. My robot's going to be able to dance, like Dancing with the Stars level quality dancing. Who knows, my robot might even be able to break dance. So my robot's just on a whole different level than what they're going for. But I'm sure if they wanted to make a robot as sophisticated and capable as what I'm going for, they could definitely do that too. Do you look for ideas from their designs for your robot? Yeah, I do. And I'm always looking for ways that I could improve. Um, but unfortunately, I haven't seen any designs that I thought were worth like using for mine in a long time. Because I've spent so many years designing mine and improving on the designs and looking at other people's designs for inspiration that my designs have become really fine-tuned and perfected to the point where um, it's hard to find something better at this point. It's basically a better design than most designs I'll see on YouTube. But there could be like secret government robots with secret designs that are like mind-blowingly better than what I've designed. But as far as like open source robots where they're showing the designs, I'm not really finding anything on the same level. Because people just want to make simple robots, like a 2-month project, a simple robot hand, just like a toy. There's not many people trying to make a robot that's actually like a real life data from Star Trek level engineering type thing. So it's just hard to find something at that complexity level that could help me take my project to the next level. So I'm kind of on my own. I feel like I'm pioneering without much help from a design perspective. Alright guys, well I've been talking for a while now. I did about an hour update. So peace out guys. I'll upload this to my YouTube channel if I want to keep some aspects of it. Alright, peace out. Have a good night.